Hello and welcome to Explore, where today we're going to take a closer look at weather and ask ourselves the big picture question, how is weather created? To those of you who've already sent us your advanced questions and your responses to our pre-program activities, thanks very much. We look forward to working those into the show. In addition, we look forward to everybody's email questions just as you watch today. Don't forget you can email us at live@hectv.org. That's live@hectv.org. And if you're watching on the web, just send them in that email window that has popped up on your screen. So what is weather? Well, maybe that's what we should start with. A question about the word itself. Let's look at that definition of weather. Weather is the state of the atmosphere at any point in time. It refers to the rain and the moisture and the clouds or lack thereof and the temperature, high or low, hot or cold, that's happening on a certain day. Weather changes constantly. Weather changes due to all sorts of atmospheric forces. So some days you have a sunny day, some days you have cloudy days, some days it's 95, some days it's 32, some days there's rain, some days there's snow. Sometimes that rain becomes so intense it's a thunderstorm. Sometimes the snow becomes a blizzard. And sometimes those thunderstorms build up and create tornadoes. We're going to have the chance today to explore how all that works with our special guest, Wes Browning, who's the chief meteorologist at the National Weather Service station in Weldon Spring, located just a few miles from our TV station here. Weather changes constantly, but another word we need to understand, climate, relates to weather but is a little bit different. Climate refers to those atmospheric conditions over time that prevail in a certain region over time. So it's what is that temperature over a long period of time? What is the state of the cloudiness or lack thereof, the amount of moisture or lack of moisture that relates to that area over time? Why there's temperate zones, why there's desert areas, all of that is climate. Remember, weather changes constantly, climate stays the same. Now, if you're a person who studies weather, then that means you're one of the people who's our third vocabulary word today. You study meteorology. Meteorology is the study of those atmospheric forces. And what meteorologists are always trying to do is to explain what's going to happen in weather and let you understand it. They do it through a variety of pieces of technology, and they end up creating all these kinds of maps. So you see all sorts of weather maps with thermal lines, temperature lines. You see radar images where there's tornadoes or where there might be snowstorms or heavier or lesser rain. All of that is different ways that explain how weather is going to come into your area. And meteorologists are going to explain that to you. Wes Browning is going to have the opportunity to talk about that today when we meet him later in the program. Our fourth vocabulary word that really matters to us is something called hydrology. Hydrology is the study of how atmospheric forces move moisture around. You've probably heard of that hydrological cycle. Moisture works throughout the atmosphere. Sometimes it's rain, sometimes it's dew. Clouds go up in the atmosphere or formed by the moisture. Then they let that moisture come back down in the form of rain, and it just goes up and down and all around, and that's how our weather gets created. We're going to look at that today as well. So we're hoping you'll enjoy the exploration as much as we will. As always, we're going to look through the question in a variety of different ways by asking our who, what, where, when, why, and how questions. First, let's look at a little history of weather and some fascinating and bizarre weather events because, trust me, weather can be truly fascinating. Let's find out some interesting events in weather and some interesting weather events.
Circa 80 AD.
In his critical essays, the Han Dynasty Chinese philosopher Wang Chong dispels the myth of rain coming from the heavens and states that rain is evaporated from water on the earth into the air and forms clouds, stating that clouds condense into rain and also form dew.
1441.
Prince Munjong invents the first standardized rain gauge. These were sent throughout the Joseon Dynasty of Korea as an official tool to assess land taxes based upon a farmer's potential harvest.
1643.
Evangelista Torricelli invents the Mercury Barometer for measuring atmospheric pressure. He perfected the instrument by conducting experiments in the Alp Mountains.
1654.
Ferdinando II de' Medici sponsors the first weather observing network. It consisted of meteorological stations in 10 cities across Europe. Collected data was sent centrally to Florence at regular time intervals.
1686.
Edmund Halley presents a systematic study of the trade winds and monsoons and identifies solar heating as the cause of atmospheric motions. He also establishes the relationship between barometric pressure and height above sea level.
Fascinating weather events. April 12th, 1934.
Winds reach 231 miles per hour on Mount Washington, New Hampshire.
July 22nd, 1918.
One lightning strike kills 504 sheep in Wasatch National Park, Utah.
July 17th, 1942.
3 feet of rain falls in Pennsylvania. That's right, 3 feet. One day.
July 6th, 1928.
World's largest hailstone, 1.5 pounds, 17 inches in diameter. 17 inches falls in Potter, Nebraska. You've probably heard the phrase, "It's raining cats and dogs," but have you heard about the torrential rainstorm that fell on Charleston, South Carolina on
July 2nd, 1843.
When the storm subsided, residents at the corner of Wentworth and Anson Streets found themselves face to face with an alligator. As Charles Pinckney, editor of the Charleston Mercury, wrote,
We have not been lucky enough to find anyone who saw him come down. But the important fact that he was there is incontestable. And as he couldn't have gotten there any other way, it was unanimously decided that he rained down. Fascinating weather events. (1724).
Gabriel Fahrenheit creates a reliable scale for measuring temperature with a mercury-type thermometer. 18 years later, Anders Celsius, a Swedish astronomer, proposed the Celsius temperature scale we know today.
1783.
Water-absorbing properties of hair were used to develop the first hygrometer, an instrument for measuring humidity. The inventor was Horace Benedict Saussure. This old-fashioned hygrometer was calibrated by first determining the length of hair at total dehydration, 0% humidity, and total saturation, 100% humidity. Relative humidity then could be calculated by using these two set points.
1846.
Dr. John Thomas Rodney Robinson invents the cup anemometer for measuring the speed of the wind.
1870.
The U.S. Weather Bureau is founded.
1959.
The first weather satellite, Vanguard 2, is launched on February 17th. It had difficulty maintaining its orbit, but very quickly other weather satellites were launched and changed the way we could forecast weather. So there you have it, some fascinating weather events and important events in weather history. We're looking forward to you interacting with our guest today, Wes Browning. So remember, if you want to send us email questions during the program, it's live@hectv.org. That's live@hectv.org. Obviously, if you're watching on the web, then the little window has popped up and you can send the questions in that way. And for our interactive school, we're going to get the chance to talk to in just a few minutes, St. Pius X in Dallas, Texas. We're looking forward to our interaction as well. Let's meet the man I've mentioned, but you haven't gotten the chance to see yet, Wes Browning, the meteorologist in charge at the National Weather Service Station in St. Louis out in Weldon Spring. Wes, thanks so much for being here today.
My pleasure, Tim.
Glad to have you. Well, we have right up here on the screen a nice map which shows everybody the location of where you guys are and the area that you serve.
Right. We're one of 122 offices across the country that forecast and warn for weather across the country. We're located right here in St. Louis. Here's the Mississippi River, and we cover 45 counties that cover a large part of Missouri and Illinois with forecasts, watches, and warnings.
So you're providing the weather forecast for those folks, and then somebody who lives, let's say, in Columbia, a bit further to our west, is getting information from a different weather service station.
Exactly. There's a weather station in Kansas City, there's one in Springfield, Missouri, one in Lincoln, Illinois, and one down in Paducah, Kentucky.
Well, our friends are joining us from Dallas. Do you know off the top of your head, I'll put you on the spot, what's the closest weather station to them?
I do know that because I used to work there in Dallas, Texas, a long time ago, about 20 years ago. The forecast office is on the northwest side of Fort Worth.
Oh, very cool. Well, we're going to talk about some of those tools and instruments that Wes gets to use every day, and we know you had some questions that we're going to ask as well. I want to begin by just talking in general about the ways that they forecast the weather and the variety of tools that they have. As we see up here on the screen again, you use a lot of different instruments and techniques to make sure you understand the weather and can share it with others.
Exactly, and that's critical, Tim, that we get a really good understanding of the current state of the atmosphere before we can have any hope of forecasting accurately what's going to happen in the future. So we use a lot of instruments, surface observations, we look at radars, upper air observations with weather balloons that are released once every 12 hours across much of the country. And then we put all of that information basically into these very, very complex computer programs that run out in the future and take all of that initial information and then use these very fancy computer programs to forecast the future state of the atmosphere, and that's the forecast.
Oh, very cool. We've gotten some advanced questions specifically from our students in Dallas about some of these instruments, and you just mentioned weather balloons. So let's go down to St. Pius X in Dallas, because I know that I believe it's Diana had a question that she wanted to ask. So go right ahead, Diana.
Why does the weather balloon expand as it gets higher?
That's a great question, Diana. And as the balloon goes up in the atmospheric pressure outside of the balloon, it actually decreases. You know when you're driving in a car, maybe in the mountains, and sometimes your ears pop? That's because the pressure is decreasing outside, and it's staying the same basically in your head. Well, think of the balloon the same way. The pressure in the balloon is staying the same. The pressure outside the balloon is decreasing, so the pressure inside pushes out on the walls of that balloon, so it expands as it goes up in the atmosphere. It gets bigger and bigger and bigger. What you may not know, by the time the balloon actually pops or explodes, when it gets about 50 to 70,000 feet in the atmosphere, sometimes it is the size of a 3-story house. Wow. It gets to be enormous, and then it pops and it floats down to the surface.
Very cool. That's a great question, Diana. And I know Sophia had another question about the use of weather instruments as well. So Sophia, let's hear from you.
Do multiple forecasters study the same weather, and if their forecasts are different, how do they decide which one to use?
I think that's a fantastic question. Kind of intimates the idea that, all right, how come we always don't have the weather right, Wes? But we won't talk about that yet. We've got a picture up here of what are called climate models. Does that help answer Sophia's question?
It does, in part. First, we look at a lot of different types of computer models, these fancy computer programs that predict the future state of the atmosphere. This is just one element that I'm going to illustrate that with here. Here's the state of Missouri. These are two forecasts, two different computer models forecasting 24 hours worth of rainfall. Here it's only showing about 1/10 of an inch. Here, 3 inches of rainfall, so very different forecasts. We get about 6 to 8 of these computer models. The forecasters then have to look at this and use their experience and knowledge of how these computer programs work to decide which one or combination of those is going to be the best forecast. Now, individual forecasts will vary across the country, and we have to coordinate with our sister offices in, like I said, Paducah, Springfield, and Kansas City. So we actually have an electronic email private chat going on constantly, and we'll basically go back and forth between the forecasters. Sometimes the conversation gets pretty spirited, though, I'll have to say.
Oh, that's a great question, Sophia. Thanks very much for that. And so, but the goal is that the forecast stations that are dealing with, let's say, the state of Missouri or this general area would basically be sending out the same general information?
Absolutely. We meld the forecasts into one map. This should look seamless to the customers.
Very cool. One of the very interesting instruments, obviously, that meteorologists are using all the time is radar. Something that was developed in the late 1930s, the 1940s, became important, obviously, during World War II. You can see planes on radar, but you can also see weather on radar. And radar has changed over the years. There's now something called Doppler radar that does really cool stuff. Well, in our segment called How Does That Work?, we want to give you an idea to understand how radar works. So let's find that out.
The radar collects data by sending a radio signal out to a target. The signal bounces off the target, raindrops in this case, and returns to the radar. The returned signal conveys 3 important properties of the target. First, the time it takes for the signal to bounce off the target and return determines the distance from the target to the radar, and thus the location of the storm. Second, the strength of the return signal, also known as reflectivity, is proportional to the size and number of raindrops in the storm. Third, the frequency of the return signal reveals whether the winds are moving toward or away from the radar, as well as their speeds. Combination of speed and direction is called velocity. The data is converted into visual images and used by the National Weather Service forecasters, the Federal Aviation Administration, and the military to provide weather support to the nation. In addition, selected visual images are made available on the web and shown on TV weather broadcasts.
And that's how obviously you get to see the weather. If you go to weather.gov or any sorts of places, you can see those kinds of radar images all the time. One of the really cool things that Doppler radar is able to do now relates to something called dual polarization. Is that a cool phrase or what? Dual polarization. And that's what this image is showing. Let's describe to the students what happens. How does it really work when this radar is showing you stuff?
Really simplistically, it's sending out two separate beams. One is oriented horizontally and one is oriented vertically. So with that addition of that extra beam, now we can actually see slight shifts in what we call the phase, or the peak-to-peak distance between these two, as the radar then is receiving this energy that's bounced back from snow, hail, or rain in the thunderstorm. And how we use that is it can give us an idea of the shape of what these objects are that are bouncing back that energy. Very important, because sometimes, especially if we're trying to warn on a tornado, we see a very violent circulation, we can actually image debris now in the storm. It gives us a lot of confidence, and in fact, there is a tornado on the ground.
Well, let's look at some of those images you referred to. I can switch the images right here on screen, and we can see that happen. So we see just your basic everyday radar image, and we notice that it's got different colors. The red and the yellow are more intense, the green and the blue are lighter. Is that the basic idea?
That's correct. The red and the orange colors enter here are returning a lot of energy, so we think that there's either hail or very heavy rainfall in those returns.
Very cool. And when we go to the next one, we're beginning to see radar images move towards St. Louis. So you'll see as the storm come in from the west here, and as we go to the next image, you'll see that it just comes in a little bit closer. And then as we go to the next image, we're really on the radar now, and we're going to see these two storm fronts converge. Let's talk about the difference between what I see in red and what I see in green, Wes.
Okay, the red basically is going away from the radar, and the green is moving toward the radar. The reason why that's important as we look at the next few images is you can see that that will change, and it'll tell us that there's a good indication then that there's probably rotation in this storm.
So notice this. We'll just show them right here on the screen as we go through this. Look at this spot and see what's going to happen to it. We go to the next image. Look at that same spot. See how things are beginning to clash and move in a little different way, what Wes was referring to as that rotation idea. Go to the next image, and now we actually have it highlighted. What's highlighted there, Wes?
Actually, you can see a very tight rotation. If you put a pencil in this, the radar's over here. If you put a pencil, it would tend to turn like this. This is coming toward the radar. This is moving away. Again, giving us a good idea there's rotation in that storm located in this area where this hook echo is. Probably a tornado on the ground right there.
Very cool, and that's exactly what we see on our next image where we've got the debris ball you mentioned before.
Exactly. This was coming in toward the airport, toward the St. Louis airport that night, and the operator actually saw this very, very intense reflectivity echo right there. That's not just raindrops or hail, Tim. That's actually pieces of people's homes, leaves, branches, maybe even bicycles, lofted into this storm up to 5,000 to 10,000 feet. It was a very strong tornado on the ground then.
Wow. All those tools that meteorologists are able to use to make sure you understand the weather as effectively as possible. We also want you to get a sense about how geography affects the weather. There's all sorts of different locations around the world that have different kinds of weather just because of where they're located. So let's go to our segment called Where Is That? And find out about the relationship between geography and weather. Our journey begins by traveling east to the Lut Desert in Iran, home to the hottest land surface on Earth. Located at 31 degrees 30 minutes north latitude and 58 degrees 0 minutes east longitude, the desert plateau is covered in dark lava
that raises the surface temperature of the land to as high as 70 degrees centigrade, 159 degrees Fahrenheit. Whew, the hottest temperature ever recorded on Earth. Whew, wow, it's getting hot in here. So let's leave the searing heat of a Middle Eastern desert and travel further east and further north to Yakutsk, Russia. The residents of this northern Siberian city, located at 62 degrees 3 minutes north latitude and 129 degrees 67 minutes east longitude, call it the coldest city in the world. And with good reason. It hit a low of negative 64 degrees centigrade in February 1891, and the average winter high temperatures are rarely above negative 30 degrees centigrade. But Yakutsk is no isolated outpost. It is the largest city built on permafrost, a thriving metropolis with a population of 270,000 people and major cultural institutions. Feel the need to warm back up? Let's head south, toward the equator, to the island of Sumbawa, Indonesia, where we find Mount Tambora. It was here, in April 1815, over the course of 10 days, when this volcano exploded and spewed millions of tons of dust, ash, and sulfur dioxide into the atmosphere, dropping average global temperatures over 1 degree Fahrenheit and creating havoc with the weather. So much so that the next year, 1816, was known as the year without summer. Americans experienced snows in June, freezing temperatures in July, and a killer frost in August. Speaking of cold weather, when we travel back to the United States, we land in Buffalo, New York, home to many lake-effect snowstorms. From November 13th to 21st, 2014, parts of the Buffalo metropolitan area received 5 to 7 feet of snowfall from such a weather phenomenon. Travelers were stuck on the highway, professional football and hockey games were canceled, and roofs collapsed under the weight of the snow. So let's head back west now to St. Louis, Missouri, where just west of the city in Weldon Spring, you'll find a National Weather Service Forecast Center, the place where our guest, meteorologist Wes Branning, and his fellow scientists keep track of the weather for the St. Louis metropolitan area. So there's some interesting information between geography and weather. And Wes, one of the things I think is fascinating there is that explosion of that volcano, because it spewed so much stuff into the atmosphere, it literally changed what was going to happen with the hydrologic cycle. Is that what occurred?
Actually, what happened is it shoots a big, huge plume of gas very high in the atmosphere, and that sulfur dioxide combines with water vapor to form little droplets of sulfuric acid. Those act like tiny mirrors, and they reflect the sun's energy coming out, so it cools the earth.
Very cool. Well, we're going to begin to talk a little bit more about the hydrologic cycle because we got some questions from St. Pius X in Dallas that deal with rain and thunderstorms and all that good stuff. So let's go back to Dallas and let's find out. I'm going to try to pronounce it correctly, but let me know if I'm mispronouncing it. Is it Yesenia? Please tell me so if I'm right or wrong.
You're right. How do you calculate how much rain will fall?
I think that's a super question. So as we look at this image here of the hydrologic cycle, which gives us just a general idea that we know we're dealing with this evapotranspiration thing, how do you take the knowledge of that and what you're learning from those other instruments we talked about and figured out, oh, it is going to be 1 to 2 inches of rain next week?
Right, again, a great question. And we look at those computer models that I talked about earlier, those very sophisticated numerical computer models. And they will tell us what their first guess is as to how much rain is going to fall over a period of time, let's say 24 hours. The key, though, is that we get a lot of different answers from those. It could range from maybe 1/10 of an inch up to several inches, and that makes a huge difference in people's lives, like farmers or someone just commuting to the mall. 3 inches of rain could be a big deal, whereas maybe not for 1/10 of an inch.
Very cool. So we'll go through some of these images. You'll see the hydrologic cycle there, and we see a big cumulus cloud building up here. As we see this cumulus cloud begin to develop and rain beginning to fall, and we've got some video of rain we can show as well at any point in time just to let everybody see how this all works out. What causes this cloud to build and do its thing?
You get heating of the atmosphere. The sun comes out and heats up the atmosphere right along the surface of the Earth. And you get this bubble of warm air, and it tends to rise. As that warm air rises, it cools as it goes up into the atmosphere. And as that atmosphere cools, you tend to form, you go from water vapor to actually little water droplets, liquid water droplets. And that's what a cloud is. And as that continues to rise farther and farther up, the cloud grows in height, more and more water forms, some hail, and then it starts to get so heavy that it drops out in the form of precipitation.
Well, and a lot of times with that precipitation, we also get something else happening in clouds, and that, in terms of Dallas's question, is what Brianna, am I pronouncing that correctly? Brianna wants to ask. Brianna, go right ahead.
Lightning come out of clouds.
How does lightning come out of clouds?
That is a terrific question, Brianna, and actually it's a very fascinating process. Lightning actually builds up from the ground and down from the clouds simultaneously. So what first happens is it forms what we call a bridge. It's kind of a weak area in the atmosphere, in the basically the electrical field. And you may be standing out sometimes and you can actually feel maybe your hair start to stand on end. If you've ever felt that, that means that lightning is going to strike very close to you. So it forms that weakness in the atmosphere and then it discharges very violently. And that's what an actual lightning strike is.
Okay. Wow. So electricity happening in the atmosphere. Ben Franklin.
Right, exactly.
So learn about Ben Franklin, keys and electricity, but don't do that at home yourself. We also had some questions about tornadoes,
okay.
And we've also got an internet question that's come in I want to ask too once we go to Paisley. So Paisley, let's find out your question.
How do you know for sure when to ring the sirens for the tornado warning?
I think that's a super question, because the internet question we got from Susie was, how come sometimes the sirens are going off in my area even though there doesn't seem like there's anything that's a tornado about to happen? So let's talk about how you determine, hey, it's bad enough storm, we need to warn people this way.
Right, a really good question, especially for those of you down in areas like Fort Worth and Dallas, where you know exactly what a tornado threat is. We tend to look at these storms with a very critical eye when we're in the office, and we can only see so much of what's going on in that storm. We can tell you whether or not it's rotating violently, but a lot of times we really depend on eyes on the ground, on law enforcement, on the public, calling us up and telling us yes or no, there is a tornado on the ground. If we see violent rotation and the atmospheric conditions are conducive for tornadoes, we'll normally issue a tornado warning. So about half the time, there probably will not be a tornado, but better safe than sorry, right? If the sirens go off, you need to get to your safe place.
Very cool. We've got some other images as we talk about thunderstorms and lightning, which lead to tornadoes as well. This is what's known as a big supercell thunderstorm, which potentially is going to create that kind of tornado. And we hear these things called downbursts. Are they the same thing as a tornado, or is it something different?
Something very different.
Okay.
A tornado is a very violently rotating column of air that's usually not more than maybe half a mile wide. A downburst is just this violent gush of air that comes down, usually with a big rain shaft, a big gush of rain that's coming down. And that's air that's cool. You know, if you stand in front of the freezer and open up the top of your refrigerator, the top of the freezer, you feel that gush of cold air sometimes coming out. It's the same thing, but this is coming out of the thunderstorm and it reaches the ground and then flows out in a horizontal way. So, for instance, if an aircraft is coming in here, they need to know the winds are going like this as they approach this storm and then pushing this way away from the storm. That would be a downburst.
So you provide weather predictions and weather forecasts specifically for aviation as well. That would be additional information than what I might get.
Absolutely. We do that as part of the core function of our job. We actually forecast cloud heights, wind speeds, and precipitation for specific airports all across the country.
Very cool. Wes, thanks so much for being with us today.
You're welcome. My pleasure.
We're going to leave in just a few seconds our web and TV audience, but don't forget our video conference connections. We've got 10 minutes of extra video conference question time for you guys, so we look forward to that. But to our TV and web audience, we want to thank you for joining us today. We want to thank Wes Browning for being here and the great folks at the National Weather Service station out in Weldon Spring who provided all sorts of wonderful video and pictures for us. We're going to explore some more weather again. We look forward to seeing you guys in another program soon. Bye-bye.